This is the third lecture that sort of form a group together. And in lecture 7, we talked about the electronic band structure. And then in lecture 8, we talked about direct band gaps. So then obviously what we do today is that we want to talk about indirect gaps. And that's one topic. And the second topic is we talk about critical points and Van Hove singularities. The simpler examples are from Mark Fox's book on optical properties, but then the more in-depth material is taken from Ewan Cardona and also from some original papers where I will give you the references. So we will start by looking at the indirect gaps in silicon and germanium. And then I will show you some experimental techniques to measure absorption coefficients. And then we will go to the second part of the lecture where we introduce Van Hove singularities in the joint density of states and critical points, and how can we use how can we fit these types of critical points using analytical line shapes. So in the last lecture, we discussed direct transitions in materials like gallium arsenide, and for a direct transition, the crystal momentum of the initial state and the crystal momentum of the final state are equal, and therefore there is no momentum transfer because the final and the initial state have the same crystal momentum. So this is gallium arsenide. Now in germanium, the L minimum, the conduction band minimum at the L point, is the lowest minimum in the conduction band, and the L minimum is lower than the gamma minimum or the X minimum. And therefore, the lowest absorption process that can occur in germanium goes from the top of the valence band at the gamma point to the minimum of the conduction band at the L point. So in this case, the initial state and the final state have a different wave vector, have different crystal momentum, and therefore we call that an indirect transition. And that will be the first half of today's lecture. So let's look at this in more detail. So this is the direct absorption process where the final and the initial state have the same wave vector. And such a transition conserves crystal momentum, whereas for an indirect transition, this is a two-step process. And here the initial state and the final state have a different wave vector, and therefore, remember, we have an infinite crystal, we have an infinite periodic crystal, and therefore crystal momentum is a conserved quantum number. And to conserve that quantum number, the final wave vector needs to be equal to the initial wave vector plus or minus some other excitation which helps us to conserve momentum. Now there is a difference between momentum and crystal momentum. Crystal momentum means that two wave vectors are identical if they only differ by a reciprocal lattice vector. So we also need to take into account that perhaps the initial and final state plus minus this momentum conserving second process differ by a reciprocal lattice vector. So we could start the transition on one side of the Brillouin zone and end up at the other side of the Brillouin zone, because these two points at opposite ends of the Brillouin zone only differ by a reciprocal lattice vector. So that's why we have this plus minus g reciprocal lattice vector. This is called an Umklapp process. So the the optical process, the optical matrix element, because the wave vector of the phonon is very small, an optical process can only go vertically in the Brillouin zone, and then we need something else which helps us with the momentum conservation. So typically, this second process is the absorption or emission of a lattice vibration of a phonon. But sometimes we can also have the momentum transfer accomplished through an impurity or with alloy scattering. So if we have a nanoparticle, or if we have an alloy of silicon and germanium, or gallium arsenide and aluminum arsenide, then sometimes this condition for the momentum conservation can be relaxed because of impurities or alloys. But if we look strictly at a pure crystal, at a pure with complete translational invariance, then this momentum conservation is required in the process. So on this slide, we want to look in more detail at indirect transitions in silicon. And in this graph, we plot the absorption coefficient of silicon and gallium arsenide as a function of photon energy. And the first thing you see is that in gallium arsenide, where we have direct transitions give us much larger absorption coefficients than indirect transitions. So the dotted line here, that is gallium arsenide, and the absorption coefficient is like 10 to the 4th inverse centimeters. Whereas for silicon, where we only have the indirect processes, indirect absorption coefficients are much smaller. So that's the first thing that's different, because why is indirect absorption smaller than direct absorption? And the answer is because it's a second order quantum mechanical process, so it has to be weaker because we need this, these two particles. We need the photon and the phonon in order to accomplish the indirect transition. So in silicon, if the initial state is an electron here in the valence band, and now there are two different processes that can occur. So either this electron first is raised into an intermediate state in the conduction band and then scatters by a phonon to end up in the final state. So in this case, this is an electron-phonon process. And the second possibility is that the electron first scatters through a phonon into a different state in the valence band and then is raised through a photon absorption into the final state, into the conduction band. So there are two different pathways that we need to consider, one using electrons and one using holes. What you will see is that this transition, this phonon scattering, does not conserve energy. So this is a second order quantum mechanical process. There is an intermediate state here. This intermediate state does not have the right energy. And therefore, if we do the calculation in quantum mechanical perturbation theory, there are some energy denominators. And the magnitude of these energy denominators, how large is the energy mismatch for this transition? The magnitude of this energy denominator determines how likely it is for this process to happen. And for silicon, both of these processes for the electron pathway and the hole pathway have about the same energy denominator, and therefore both of these processes are possible for silicon. But when we go to germanium, then we'll see that this will be different. So the entire process needs to conserve energy. So the energy of the final state needs to be equal to the energy of the initial state plus the energy of the photon plus or minus the energy of the phonon. So here there's a plus or minus because the phonon can either be absorbed or emitted, and therefore we have these two sign options. And of course, crystal momentum also needs to be conserved. And if we do the calculation, and I will show you a paper in a minute where this calculation was actually performed. So if we do this calculation, then we see that the absorption coefficient for an indirect process goes like the square of the photon energy minus the band gap plus or minus the phonon energy. If you remember direct transitions, for direct transitions, the absorption coefficient goes like the square root of this energy difference. But for indirect transitions, it goes like the square of the energy difference. So germanium is different, and perhaps you can already see here that the energy mismatch for the hole-assisted process, here the energy denominator is much larger, so this dashed process, which involves holes, can be ignored for germanium. On the other hand, the energy denominator for the electron process is much smaller, and therefore the electron phonon assisted process is the dominant one. Because the absorption coefficient increases like the square of this energy mismatch, what we do is we plot the square root. We plot the square root of the absorption coefficient, and that increases linearly with energy. So this plot is shown here. This is the square root of the absorption coefficient of germanium as a function of energy, and both at 20 Kelvin and at near room temperature. And if the sample is at 20 Kelvin, then the temperature of the sample is too small to have a strong thermal occupation of optical phonons, and therefore we only can have phonon emission. And therefore, if we plot square root of alpha versus energy, then we get a nice straight line at low temperatures. And from this, we can determine the approximate location of the indirect gap. But remember, now we have to consider that the final state energy is actually the initial state energy plus the photon energy plus minus the phonon energy. So this is not exactly the band gap, but the band gap needs to be shifted in order to take into account that the energy here is the band gap plus the phonon energy. So we need to subtract the phonon energy in order to get the actual band gap. At room temperature, we have a significant occupation of phonons, and therefore electrons can not only emit phonons, they can also absorb phonons. And therefore we see this tail here, which is coming from the phonon absorption, and we will zoom in on that and with higher resolution in a minute. So in order to get indirect gaps, we plot the square root of the absorption coefficient versus energy, and then the slope tells us something about the band gap. Now the same data that are shown here are plotted again on the right-hand side. Again, this is room temperature absorption for germanium, but now instead of plotting square root of alpha, we plot alpha, and we also change the scale. So these data points here, the absorption is very, very small. So these data points here, they're almost zero. And we really have to blow up the scale in order to find the indirect band gap. And then here between 0.65 and 0.8 eV, we only have indirect transitions. Therefore, the absorption coefficient is very small. And then here at 0.8 eV, where the direct gap is located, all of a sudden we can also make direct transitions, and therefore the absorption coefficient increases very rapidly. So at low energies, we only have the indirect transitions, and then at higher energies, the direct transitions are also possible. And sometimes people ask me, well, how can you determine the direct gap of germanium because it is an indirect material? Well, obviously, I need to look at a different range. And I see that at first, there's only indirect transitions, and then after a certain threshold, there is another increase, significant increase, and that tells me about the direct band gap of this indirect material, germanium. So in order to make this indirect transition, we need assistance from a phonon. So we look at the phonon dispersion relation of germanium, and then we ask ourselves, well, which phonon do we need? Well, because the conduction band minimum is located at the L point, we know that we need an L point phonon in order to achieve the crystal momentum conservation. So let's look at the dispersion relation for germanium. Let's look at the phonons at the L point. And there is a transverse acoustic phonon, there's a longitudinal acoustic phonon, and then we have a longitudinal optical phonon and, of course, two transverse optical phonons. So we have 1, 2, 3, 4 phonons. Which of these phonons is responsible for the indirect transitions? Which of these phonons assists? And the answer is that it's the longitudinal acoustic phonon, this one here, which helps with the indirect transitions in germanium. And why is that? Well, we need to look at group theory, and there is a paper by Joe Berman, 1962, which explains that. So the initial electron state, if we look at the band structure, do I have a band structure somewhere? The initial, I'm sorry, yeah, here. So the intermediate state has gamma 2 prime symmetry, and the final state has L1 symmetry. So we need a phonon which can bring us from a gamma 2 prime state to an L1 state. And therefore, we take the dyadic product of the initial electron state with the final electron state, and we take this product and we write this product representation. We decompose it into irreducible representations. So this dyadic product of the initial electron state and the final electron state, that gives us this representation L2 prime. And that is the LA phonon. And using group theory, we therefore know that only the L2 prime, only the longitudinal acoustic phonon can contribute. That is only true approximately. And the reason it's only true approximately is because we have calculated the matrix element from the high symmetry point gamma to the high symmetry point L. But as soon as we are going away from the immediate band gap, we walk away in the Brillouin zone from the high symmetry point, and therefore the selection rules are no longer valid, and we can assume that some other phonons may also contribute the more, the further we go away from the gamma point. And therefore, what people calculate is one calculates these intervally phonon spectral functions. So here this is the phonon dispersion relation, and rather than plotting the phonon energy versus wave vector, what we can also do is we can plot the density of states of the phonons, where we plot how many phonons are there for a given energy, and then that would be a density of states. But this is a spectral density of states, where we multiply the density of states with the probability that the phonon at that energy will contribute to an intervally scattering process. So this is not germanium, this is gallium arsenide. Gallium arsenide is almost the same as germanium, except that there is a small dipole moment between the gallium and the arsenic. And therefore, many of the selection rules which are true, which are valid in germanium, are also still valid in gallium arsenide. And if we plot this intervally spectral function, then we see that the longitudinal acoustic phonon has the strongest contribution. But we also have contributions from the longitudinal optical phonon. That is because of the loss of the inversion symmetry, because now the LA and LO phonons have the same symmetry. But we also see these transverse phonons make a contribution. And the reason for that is because we've walked away from the high symmetry points. And therefore, there will also be a small contribution from the TA phonons. So group theory can tell us qualitatively which processes are the most likely, but then in order to get an actual, in order to get the actual importance of each phonon, we need to do this calculation of the matrix elements using the phonon eigenvectors and using the wave functions for the electron states. So this process here is assisted primarily by longitudinal acoustic phonons. The Hole-assisted process, this state here has symmetries of the states in the Hole bands are different, and therefore the LO phonons are actually responsible for the Hole phonon scattering, but we can ignore this process with the holes because the energy denominator is much larger. So this picture here does not have a very high resolution, the indirect transitions in germanium. So this figure is from Yu and Cardona, where the square root of the absorption coefficient is plotted versus photon energy with better resolution, and you clearly see you come down at, what is it, 195 Kelvin. There's a nice linear contribution from the phonon emission, and then there is this kink, because now we have to consider not just the phonon emission but also the absorption. I'm sorry, this is for silicon. Germanium is here on the right, and you see that the square root of the absorption coefficient is anything other than linear. And that has to do with the fact that there are several phonons that contribute to the indirect absorption process. And each of these kinks, one can blow up the data and one can still see contributions from various phonons. And in germanium, there's definitely a lot of different phonons contributing. In gallium phosphide, the process is even stronger, and we can see the various contributions of LO and TO phonons and transverse acoustic phonons and longitudinal acoustic phonons, and we can even have two phonon processes contributing to the indirect transition of gallium phosphide. So determining the actual indirect band gap can be very complicated unless one performs very high resolution measurements and is able to attribute the various phonons to the features that are observed in the spectra. These measurements are absorption measurements. As I may have mentioned, it is possible to do modulation spectroscopy measurements, and there is a paper here which uses wavelength modulation to measure the derivative of the absorption coefficient with respect to photon energy, and then you see peaks much more clearly in the modulation spectra than in the pure absorption spectra. To measure wavelength modulation, what one could do, for example, is that one has a grating, and the grating is wiggled, and the grating turns a little bit, and then the lock-in amplifier, which detects the signal, is set to the frequency with which this grating is wiggled, and therefore one can measure the derivative of the absorption coefficient with respect to photon energy. Now, the indirect absorption of germanium, well, obviously this is a topic which was much discussed in the 1950s and 1960s, but I would like to point out that this is still an interesting topic, and there was a paper only last year about the indirect transitions in germanium, and for the first time this really was done right. Well, not quite right, but almost right. And the problem when you do absorption measurements is that you have to worry not only about the energy which is absorbed in the crystal, but also about the energy that is reflected. And so many of the early experiments ignored the reflectance losses because the refractive index of germanium was not very well known, and therefore the reflection losses couldn't be calculated very well. But now with spectroscopic ellipsometry, we know what the dielectric function is for germanium, and therefore we can calculate the reflection losses much more accurately than back in the 60s. And therefore, the absorption coefficient can be measured much more accurately today than it was in the 60s. And then, so there were new experiments that were performed by, I think, either David Lockwood or Mike Thewald, I don't remember. And then there is also, in this paper, you also have a new theory which contains all the details of the band structure, and it also includes excitonic corrections. And then the only fit parameter is the strength of this electron-phonon coupling in the valence band between the gamma and the L point. And here in this figure, you see the absorption coefficient of germanium, and you see the data together with the full theory. And this fits really very well. And the older theories from the 60s are much more difficult. The discrepancy is much larger. So I said before that if we compare the strength of direct transitions, like in gallium arsenide, with indirect transitions, then we see that the strength of direct transitions is much larger than the strength of indirect transitions. But is this always true? So here I'm showing you the imaginary part of epsilon that's sort of like the absorption coefficient. The solid line here is crystalline silicon. And you see here there is a very strong rise of the absorption coefficient in crystalline silicon at around 3.4 electron volts. And that is the onset of direct transitions. And here we have the everything below 3.4 electron volts in silicon, everything below 3.4 eV, those are all indirect transitions. So we can measure indirect transitions in materials if there is a very large difference between the indirect gap, which is somewhere around here, and the direct gap. So we have this 2 eV difference between the indirect gap and the direct gap. And therefore, we can measure indirect transitions in ellipsometry because of this large energy difference. However, with ellipsometry, we can almost never measure the indirect gap, which is over here, because for an indirect gap, the absorption coefficient is just way too small. You see, in order to get the right indirect gap, one has to measure absorption coefficients that are on the order of 0.1 inverse centimeters. So either one needs a sample which is very, very thick, maybe a meter thick, in order to measure such small absorption coefficients, or if we use ellipsometry, ellipsometry is a good technique starting at around 100 or 1,000 inverse centimeters. So up here we can measure with ellipsometry, but down here we need different experimental techniques. So in crystalline silicon we have the direct transitions at 3.4 eV, and below that we have indirect transitions. Now the dashed line shows polycrystalline or nanocrystalline silicon. And because of the small crystallinity, the rules for the conservation of crystal momentum are relaxed, and therefore the indirect transitions in nanocrystalline silicon are much stronger than in crystalline silicon. If we go to amorphous silicon, then the selection rule for crystal momentum is completely relaxed, because in amorphous silicon we no longer have any long-range ordering, and therefore in amorphous silicon we see a very different crystal spectrum, where indirect transitions, where the transitions below 3 electron volts are much stronger than in crystalline silicon. So the loss of periodicity increases the strength of the indirect transition, and the same, we can do the same if we, instead of using an amorphous material, if we study semiconductor alloys, we also see that there is a strong increase of indirect transitions. So how do we measure absorption coefficients? And there's 3 different techniques. We can do transmission measurements, we can do ellipsometry, or we can do photothermal deflection. And with a transmission measurement, we start with a white light source, and then we focus the light onto a sample which might sit in a cryostat to vary the temperature. And then the transmitted beam is focused onto a spectrometer and a silicon array detector, and then read into a computer. So this technique is very, very good for small absorption coefficients, but the problem is that we need to correctly consider reflection losses. And here this is even more difficult because the light is focused onto the sample, so the reflected light, the angle of incidence is not normal for all photons, so it's difficult to correct for reflection losses. And the other thing is that in order to measure absolute absorption coefficients, we need a reference measurement where the sample has been removed. So we need to take the sample out and not change anything else, and then divide those two results in order to get absolute absorption measurements. That is sometimes very difficult because if you take the sample out, usually something else changes with the experimental setup, and therefore with a setup like this, measuring absolute absorption coefficients may be difficult. There are also instruments which have two beam paths. So there's one beam path with sample, and then there's another beam path without the sample, and they both are recombined onto the same detector, and these double path techniques sometimes give you a better result. Down here I have a different setup, which is sort of the same principle, that you have a PIN diode, and the light is hitting this diode, and then the light is absorbed in the intrinsic region of the semiconductor and creates electron-hole pairs. And then the holes drift to one side and the electrons drift to the other side of the to the contacts, and therefore you measure a photocurrent. So if this is the negative electrode, then the holes are pulled towards the negative electrode, so you measure a current. And this photocurrent is this photocurrent depends exponentially on the absorption coefficient. So by measuring the photocurrent, you're very sensitive to where does the absorption turn on. So here you can measure the indirect gap rather accurately. The problem with photocurrent is that there may be some device physics that may be going on here, and therefore there may be some artifacts in this device which would not be present if you just measure a transmission of a bulk sample. And this is another example of a transmission measurement. So those were the first two techniques, photocurrent measurements and transmission measurements. With ellipsometry, rather than measuring the transmission, we measure the reflectance, and we come in with monochromatic light and we select a specific polarization, and then when the light is reflected, then the polarization of the light changes, and we detect the polarization state. We select the polarization state of the reflected light, for example, with a rotating analyzer, and then a detector measures the signal, and from the change in the polarization state of the reflected light, that's the this is the reflection coefficient, the complex reflection coefficient for p-polarized light, the complex reflection coefficient for s-polarized light. That's the reflectance ratio. And this reflectance ratio rho can be used to calculate the complex dielectric function if the angle of incidence phi is known. So we are getting from this reflection measurement the real and imaginary part of the dielectric function, and that imaginary part that contains information about the absorption coefficient. And these measurements are possible using commercial instruments like the ones that are here, from 30 milli-electron volts to around 8.5 electron volts. So from the mid-IR to the vacuum The third technique, and that's not used as much, is called photothermal deflection. And I looked on the internet for pictures about photothermal deflection, and I found this picture here from a university in Prague. So apparently somebody has this instrument here. So this is the sample, and you want to measure the absorption coefficient of the sample, and which is very small. The absorption coefficient is very small. So the way this works is that you have a helium neon laser, and the helium neon laser hits the sample at a very shallow angle, and the angle with which the beam is reflected depends on the temperature of the sample here at this point. So by modulating the temperature of the sample, you can move the beam back and forth across the position-sensitive detector. And now what you do is you have a white light lamp, a tungsten lamp, and you have a monochromator. You select a specific wavelength. And if the wavelength from the monochromator, if the photon energy is below the band gap of the sample, then the light will just go through and nothing will be absorbed in the sample. On the other hand, if the light is above, if the photon energy of the light hitting the sample is above the band gap, then the photon will be absorbed, and there will be a very slight increase in the temperature of that sample, and that causes the deflection of the beam. So
So is it because the sample experienced thermal expansion? Because of thermal expansion of the...
Well, there is some... I've never used this technique. So the question is where does the deflection come from? So that's a very valid question. I have never used this technique, so I'm not exactly sure about the answer. But I think the key is here, thermosensitive liquid. So probably this means that when the liquid gets warm, something changes, and that is responsible for the change in the angle. So I cannot really answer your question correctly, but if you want to know, call Jakub Holowski. I don't know who that is, and perhaps he can explain that. Did you want to mention something? Yeah.
Comments, there is change of refractive index in this liquid. And
Yes.
The refractive index changes, the beam is banded.
And that's, yes, so the comment is that the beam is bent because the refractive index of the liquid changes.
Due to temperature.
But that's exactly what I don't understand, because the angle of reflection, the angle of incidence is equal to the angle of reflection regardless of what the refractive index of the liquid is.
The beam is parallel with the surface.
Yeah.
And as there is a gradient of refractive index, the beam is bended.
Okay. Okay, so the beam is bent by a gradient in the refractive index. Now I get it. So that's the answer to your question. So that because of the gradient, the sample will heat up, and therefore there will be a gradient in the temperature profile across the liquid. And since the temperature of the liquid determines the refractive index, that explains why it is reflected.
It means that the laser beam propagates in a medium with this refractive index, and it will be effectively shift.
Yes, yes. So the gray area here, that is the liquid,
Okay.
and there will be a Schlieren effect. Sometimes you see this on the road when on a hot summer day, that the hot hits the asphalt of the road, and then there is a gradient in the temperature across the in the air, and therefore you see these slight variations in, you can see the temperature change. So in this inset, this is a film of amorphous silicon, and with regular transmission measurements, absorption coefficients can be measured down to about, what's plotted here is absorbance. So the absorbance is the product of absorption coefficient and thickness. So with regular transmission, you can measure absorbances down to about 1%. And this limit can be lowered. You can measure absorbances down to about 1 part in 1,000 with a photothermal deflection, and much smaller much smaller absorption coefficients can be measured with photocurrents, but then you're dealing with certain device physics complications that you need to take into account. So these are the 3 different measurements, or 4 different measurements that can be used to measure absorption coefficients. So that finishes the first half of the lecture about indirect transitions. And now I want to move to the second half, which has to do with Van Hove singularities. This is the band structure of germanium, and in the first half of this lecture, we discussed indirect transitions. Indirect transitions from the gamma point in the valence band to the conduction band minimum at L. So that was the indirect transition. And we also talked about direct transitions, which would occur at the gamma point from the valence band to the conduction band. But what you'll notice here is that the valence bands are almost parallel to the conduction bands for most of the gamma L direction in the Brillouin zone. So along the 1-1-1 direction from gamma to L, that's 1-1-1. So along the 1-1-1 direction, these 2 bands are parallel, and therefore direct transitions from this valence band to this conduction band along 1-1-1 are very likely to happen. Since the bands are parallel, the likelihood for these transitions is very large. So let's look at Fermi's golden rule again. The transition rate has 2 contributions. There is the square of the momentum matrix element multiplied by the joint density of states. So we talked about this momentum matrix element, and that's the K dot P matrix element. And we evaluated that, and that was probably 2 lectures ago. And then we also looked at this joint density of states, and for the direct transitions at the gamma point, this joint density of states increases like the square root of the photon energy. And you have a question?
Yes, I had this question before, but now you constantly plot these arrows with the length, with exact difference between the bottom and the top, right?
Yeah.
But what is then the benefit of the indirect? I thought like you go from that energy to this energy, and then this is less, right? You speak that when you have like the energy of photon needed for direct, transition is higher. So you have indirect is lower for photon energy.
Yes.
So could you please explain why then, what is really, the arrow should be shorter probably. You say that a photon makes just direct vertical transition, but with what energy? It can be comparable with the energy difference of the indirect transition, right?
So so your question is about when do we get direct transitions and when do we get indirect transitions?
Yes, and precisely, do we need to go to that energy minimum, or we can go below it and then kind of jump?
So whether you have an indirect transition or a direct transition depends on the energy of the photon. So the energy of the photon is fixed by the monochromator that you use for your absorption experiment. If the energy of the photon is less than the indirect gap, the photon will just go straight through, right?
Yes.
Okay. If the energy of the photon is between the indirect gap and the direct gap, in that case, only indirect transitions are possible, right? If the energy of the photon becomes larger than the direct gap, direct transitions are also possible. And at that point, because the direct transitions are 1,000 times stronger than the indirect transitions, when the photon energy exceeds this threshold, so in this regime, between the indirect gap and the direct gap, only indirect transitions are possible. But once the photon energy becomes larger than 0.8 eV, the absorption coefficient rises very fast because now direct transitions are possible. So for a photon at 0.9 eV, we no longer think about indirect transitions because they would be much weaker. Yeah?
Yeah.
So now these parallel lines go to the next step where we see, you see, so down here we only have indirect transitions. Then there's a step which gives us direct transitions. But then we also, but these direct transitions are still very, very weak compared to that transition here where we have these two peaks. So we now go to the next level we now go to the next order of magnitude. So the indirect transitions are extremely weak. These direct transitions here are relatively weak in comparison to the strong absorption that we see at even higher energies. And that's what I'm trying to explain now. Okay? So here the bands are parallel, and therefore we see these really strong peaks in the absorption coefficient. And that comes, these peaks come from the joint density of states. So the joint density of states, we defined that as a volume integral in K-space over a delta function of the energy minus the difference between the final and initial state at each point in K-space. So what is the delta function of another function? Do you remember the properties of the delta function? So what is delta of f of x? Somehow that has to do with the derivative of f. So here we can convert this volume integral over a delta function. We can convert that into a surface integral over the derivative of the energy difference between the final and initial state. So, and this is a gradient in K-space. So let's look at the meaning of this derivative for a moment. So this is the initial state, and this is the final state. And as I walk along this line in K-space, this derivative here vanishes because along 1, 1, 1, the energy does not change as the K point varies. So therefore, this derivative, this gradient in k-space is 0, and therefore what I'm integrating over here goes to infinity, and therefore this joint density of states becomes very large because the denominator becomes very, very small. So with this, so when we derived the joint density of states, the square root like onset for the direct transitions at the direct band gap, we assumed that we have this effective mass, and therefore we get this square root like onset times some power of the effective mass. But with this expression, we can calculate the absorption coefficient directly in k-space without making any assumptions about effective masses. But so this expression is accurate, and there's no effective mass in here. But nevertheless, what we do is we expand this energy difference into a Taylor series. So now we say that there is a this gradient, there is a maximum or a minimum at a certain k vector k0, and then we expand this energy in k-space around k0. And so the energy as a function of k is the energy difference at k0. And then we have this three-dimensional Taylor expansion where we only have a quadratic term. Why is there no linear term? The linear term is 0 because the gradient in k-space vanishes. So that's why the linear term is 0. And so we do this Taylor expansion. And the Taylor coefficients, there's 3 Taylor coefficients for the x, y, z directions in k-space. And if all of these a's are large, or about the same order of magnitude, then we call this a 3-dimensional critical point. On the other hand, what can happen is that one of these ai's is 0, and the other 2 are non-zero. So that would be called a 2-dimensional critical point. So depending on how many of these ai's are small or 0, that determines the dimensionality of the critical point. And then also some of these ai's may be positive and some may be negative. So we may have something like a saddle point. And that is used in the nomenclature that I will explain on the next slide. So let's look at this at the 111 region in the Brillouin zone. So as the k vector varies along 111, there is no change in the energy difference between these two bands because these two bands are parallel in the 111 direction. Therefore, this coefficient A along the 111 direction is 0. On the other hand, if you look at the k vector perpendicular to this plane, so if you look at a k vector perpendicular to 111, then there is a very strong curvature in the bands because of this saddle point. So the whole band curves down and the electron band curves up in a direction perpendicular to this 111 direction. So 2 of these ai's are very large, and the third one is 0, and therefore this structure here is a 2-dimensional critical point because because the energy does not change along one direction in k-space. So using this Taylor expansion, we can classify the critical points into 3-dimensional, 2-dimensional, or 1-dimensional critical points. There's also 0-dimensional critical points, but those are excitons, and we'll talk about those later. So the normal direct band gap that you find, for example, in gallium arsenide with a square root-like onset, that's a three-dimensional critical point. And all three masses are positive. All three of these inverse effective mass parameters are positive, and therefore we call that an M0 critical point, because that subscript 0, that tells us that 0 masses are negative. If we looked at the opposite, so an M3 critical point would be 1, where all three effective masses are negative. So such an M3 critical point, I cannot give you an experimental example for that, but it's simply a mathematical analysis of this Taylor expansion. So that's the direct gap in gallium arsenide or in germanium, the square root-like onset. What happens here along the 1, 1, 1 direction in K-space is that one of the masses is 0, therefore we have a two-dimensional critical point because only two of these coefficients are non-zero. And this is a saddle point exciton because one of the masses is negative and the other masses and the other two masses are positive. So this is a saddle point exciton, and that gives us a logarithmic singularity. And these are the two most important types of critical points of Van Hove singularities that we can find. So what does this look like experimentally? The indirect, this is for silicon, so the indirect gap of silicon is very small, and then here we see 1, 2, 3 different structures in the absorption coefficient of silicon, and this structure here is coming from, that's called the E1 critical point, is coming from the bands at 1, 1, 1, where the bands are parallel. This structure E2 is very difficult to see because it is at it is coming from a broad region of K-space with some odd coordinates that you would not normally find along the high symmetry directions that are plotted in a band structure. So silicon is almost transparent up to 3 eV, where only indirect transitions are possible. And then we see this sharp rise at the onset of the E1 transitions. And of course, because this is silicon, the Z number of silicon is very small, and therefore we see basically no spin orbit splitting in silicon. If we go to germanium, then this E1 critical point in silicon is now split by spin orbit interaction, and therefore we see these two critical points, E1 and E1 plus delta 1. So these two bands at the L point are split by the spin orbit interaction, and the splitting between these two bands is exactly the same as the splitting between these two peaks at E1 and E1 plus delta 1. There is another place in germanium here along the delta direction. The bands are also parallel, and this transition is called the E0 prime transition. That's shown here. And then we also have the E2 transitions, but like I said before, they are not at a high symmetry point or region in the Brillouin zone, and therefore I cannot show you where the E2 critical point happens, but it's somewhere near the X point. So the E2 critical point typically is about the same as the X point separation. And then we also have the E1 prime critical point, which goes from the highest valence band to the second lowest conduction band. So this is the E1 prime transition, which is occurring here at around 5.5 electron volts. So to summarize again, at the lowest photon energies, we only have indirect transitions. Then we have this little hump. That's the three-dimensional E0 critical point. And then if the photon energy increases more and more, we get these much larger, much more significant features in the absorption coefficient, which are Van Hove singularities where two bands in the Brillouin zone are parallel.
Sorry,
yeah.
Just make it clear. The 3D means the highest sensitivity in the absorption, right?
No.
So the 3D is the strongest, or this 3D is the weakest?
So the question is, what does the dimensionality of these critical points mean? So because the gradient in K-space is 0, I do a Taylor expansion where the linear term is 0 because the gradient is 0. So then I'm only keeping the second term, and because it's a Taylor expansion in a three-dimensional space, I need three Taylor coefficients, A1, A2, A3, or AX, AY, AZ. So these are the Taylor coefficients. These Taylor coefficients can be positive or negative. Or zero. So I'm classifying the critical points by the dimension of the critical points tells us how many of these coefficients are 0. And for the direct gap E0, this is a three-dimensional critical point, but on this scale I can barely see it. So the three-dimensional critical point is not the strongest one. 3D simply means that it's isotropic, and because it's isotropic, none of the three coefficients is 0. This critical point here is much, much stronger, but it's two-dimensional. Two-dimensional only means one of the coefficients is 0, the other two are non-zero. Or it's not exactly 0, but it is very small, much smaller than the other two. So the dimensionality of the critical point has nothing to do with how strong it is. So this one here is three-dimensional, this is two-dimensional, this is usually two-dimensional, this is two-dimensional. E0 prime, I'm not sure. That might be another three-dimensional one. So finding peaks can be difficult. In this case, it's very easy. But what you'll see is that the maximum in the imaginary part and the maximum in the real part are not at the same energy. And here for the E0 prime, the E0 prime is sitting on top of this linear background. So when you have a peak sitting on a linear background, it is very difficult to get the exact energy of that peak. Because as that slope changes, the energy that you see, the apparent peak energy that you see, will also move across. So therefore, we are looking for a technique to somehow sharpen these critical points and also subtract the linear background that there is. So if we take this spectrum here, epsilon versus photon energy, if we take this spectrum and we calculate the second derivative of epsilon with respect to photon energy, so the second derivative removes the linear background. So what we do is that we calculate the second derivative, and then this structure here looks like this. So now the critical points are much sharper, but where is the energy gap? Is the energy gap at the minimum, at the maximum? Should we look at the real part? Should we look at the imaginary part? with a little bit of experience for this particular point, the critical point, the energy gap is right there where the real and imaginary parts cross. But how do we know that? We have classified the critical points based on the number of zero masses and the sign of the other masses, whether they're positive or negative. And then using the Taylor coefficients AX, AY, AZ that we've mentioned before, it is possible to derive general expressions for the critical points in 1, 2, and 3 dimensions. So this expression for a 3-dimensional critical point, we expect a square root-like onset. So if n, that's the dimensionality, is 3, then I have 3 minus 2 divided by 2. So for a 3-dimensional critical point, I'm getting the expected square root-like onset. For a 1-dimensional critical point, then this would be minus, the exponent would be minus 1/2. And then this coefficient A is the amplitude of the critical point, and that has to do with these Taylor coefficients that we've had before. So the inverse effective mass parameters go in there, as long as with some fundamental physical constants. So the critical point parameters are the energy of the critical point, the broadening, the amplitude, and then this excitonic phase angle. And what does that phase angle do? You see, the M0 critical point and the M3 critical point, they're sort of the same, except that they're switched around the energy gap. There are other things that can happen based on the dimensionality. I'm plotting here the absorption coefficient epsilon 2, but sometimes because of a variety of other effects that we'll talk later, there can be a mixture of the real and imaginary parts. So even though this looks like an imaginary part, this might be something that we actually see in the real part. So this excitonic phase angle can consider excitonic effects, and it can also consider mixtures between the different types of critical points. So for a 3D M0 critical point, this angle here is 90 degrees. It should be 90 degrees, but in the experiment we actually don't always see it as 90 degrees. So that's why this phi here can have other values, and it needs to be treated as a fitting parameter. For a 2-dimensional critical point, this exponent here becomes 0, and therefore when we do the integration, when we do the math, actually we shouldn't put 0 in the exponent. This becomes a natural logarithm. So a 2-dimensional critical point is described by this logarithmic function. So we calculate the second derivative of the experimental data, and then we also calculate the second derivative of the analytical line shapes that we have derived from this Taylor expansion of the joint density of states. And then we compare the two. And here the solid lines are the second derivative of the general expressions of the analytical line shapes, and the dots are the data points. So you see there's actually a very good agreement between the model and between the analytical line shape and the experimental data. And therefore we can extract all 4 of these parameters, the amplitude, the phase angle, the energy, and the broadening. All of these 4 parameters can be extracted with very high energy, with very high accuracy. The the accuracy that we get for the energy in this particular case for the E1 energy is about 1 milli-electron volt. So that is a very, very high accuracy. And I should say that in the 70s, in the 60s and 70s, people directly measured derivatives versus photon energy using modulation spectroscopy techniques. So you can vary the temperature of the sample, you can apply an AC electric field, or do things like that. So you can actually directly measure the second or third derivative of the dielectric function versus energy, and that is described in some of these older references to modulation spectroscopy. But nowadays, because of the high accuracy of spectroscopic ellipsometry, it is usually more convenient to just do an ellipsometry experiment and then calculate the second derivative rather than doing modulation spectroscopy experiments, which are typically experimentally more involved. There are special programs that can calculate derivative and do the fits, and if anyone has any interest in that, then I can show you. So with these general expressions, they were derived from a Taylor expansion of the energy difference between the final and the initial state. So here's our Taylor expansion. And therefore, we should assume that they are accurate right at the critical point. But these Taylor expansions do not describe the linear background. They do not take into account variations of the matrix element. They do not take into account contributions from nearby critical points. And therefore, we can't really fit the complete dielectric function as a sum of these critical point contributions. We need to modify these critical point expressions to allow additional flexibility to take into account the actual dielectric function. So here, for example, this is mercury cadmium telluride, an alloy with varying cadmium compositions. And right here, right at the critical point, perhaps one can fit the data with these critical point models. So right here, this peak, that might be described by the saddle point critical point. But what about the tails? Usually when you try to fit line shapes, then the tails is what kills you. You can find the peak. But then the peak might be asymmetric. It might be different on the left or on the right. And to get a really, really good fit of the peak from over the complete spectral range, that can be very, very difficult. So Jim Garland at the University of Illinois, Chicago, was one of the first who thought about this. And he came up with this model where you describe the critical point in different regions. And he says, well, right here at the critical point, I'm using the analytical line shape. But then I'm saying that this is only valid up to a certain point here, and then to the left, I need a different equation. And the same is true here on the right, that I'm using the critical point expression up to here, and then I'm using a different type of expression on the right. So no one has ever actually written down all these equations for this, and the best place to find them are in a US patent. And if you've ever read any patents, so if equations are described by lawyers, then they're not very, it's very difficult to understand. So you find some guidance about this parametric oscillator model in these two references. But you would use about 10 parameters here for such a model, which is much larger than the 4 that we have in the critical point expression. But then the advantage is that if we use such a large number of parameters in a generalized critical point model, in this P-semi model, then we can describe the experimental data to any level of accuracy that we desire. But the price we pay is that we have this large number of parameters that nobody really understands. And these parameters are intended primarily to fit the experimental data. The parameters don't really have any significant physical meaning. And therefore, this model can be very useful at determining layer thicknesses or modeling materials. This model is used in the semiconductor industry, perhaps, to determine whether a material has been deposited properly or not. So I wanted to introduce this, even though there is very little physics, because this model is used quite a bit to analyze spectroscopic ellipsometry data. So here's my summary. We've talked about indirect gaps in silicon and germanium, and we've asked which phonons are important and how do we determine that. And we've talked about various experimental techniques to measure absorption coefficients. And then in the second half, we talked about Van Hove singularities in the joint density of states and how they appear as critical points in the dielectric function. And I've shown you an example on how analytical line shapes can be used to describe these critical points using this Taylor expansion, and how we used fits to these analytical line shapes to second derivatives. And then finally, I've shown you this parametric oscillator model, which is perhaps only of interest to a small number of people that really do spectroscopic ellipsometry. So there are 3 lectures that are left here. And then I have to go back to Las Cruces. I know what I'm going to talk about in the next lecture, so we'll talk about excitons and photoluminescence and quantum confinement, quantum wells, quantum wires, quantum dots. So here I know pretty much what I want to talk about. And then we have 2 lectures which are sort of more specialized. And I think in the last lecture, I want to talk about stress and strain and deformation potentials. But here, this lecture 11, in the beginning I said I wanted to do a lecture on anisotropy, but I've already talked a lot about anisotropy. So here, lecture 11 is sort of up to you. What would you like me to talk about? And please don't tell me bio, because I don't know anything about bio. So please send me an email. What are the things that you would like to see and that you would like me to cover? And that is everything that I wanted to say today. So if you send me an email within the next week or so, then I will have time to prepare some materials about the topic. Yes?
But this must be related to applications, or it can be anything?
No, well, applications, I meant applications of the framework that we've discussed so far. So stress and strain, I'm not going to talk about commercial applications or industrial applications, but we will apply the concepts of direct and indirect band gaps to stressed materials. That's what I meant. Okay, Do you have any questions for me other than those that were already asked? Well, if not, then yes, go ahead.
Maybe one general question. We have considered like the increase of absorption, but then there should be some decrease afterwards, right?
Yes.
So this was not much discussed. Can you please say a few words about the decrease?
Well, if you look at this critical point, it goes up and then it goes back down. So that has to do with the positive and the negative masses. And here it looks like, well, here it goes up and it looks like it will go up forever, right? So why does it not continue forever? And the reason is that this model assumes a parabolic band dispersion. So at higher energies, the mass gets larger and larger, and that will affect the rise of this onset.
But not only within the theory of these critical points, but in general, if you have some UV light, then it will be always absorbed, or it can be also transparent for UV light, say?
We talked about the transparency of alkali metals that can become transparent in the ultraviolet if the photon frequency is larger than the plasma frequency. But for a material like silicon, regardless of how far you go into the UV, the light will always be absorbed. However, as you can clearly see, there is a maximum in the absorption coefficient. And that has to do with the band structure and with the matrix elements. And just here, the maximum is so large because the Van Hove singularity is so strong. And as we have seen here, Van Hove singularities not only give you an onset in the absorption, they also give you peaks in the absorption. You also see that here. There's a peak here. There's a peak here. So Van Hove singularities can give you peaks in the absorption. And therefore, for silicon, as you exceed the E2 energy, the absorption coefficient goes down again.
I will also add a question.
Yes.
Is there any experimental technique to investigate UV absorption beyond tens of electron volts?
So the question is, how do I measure absorption coefficients at energies that go beyond 8.5 electron volts? So, which you can do in this building. So, with a regular ellipsometer, you can measure up to about 6.5 electron volts. Above 6.5 electron volts, air will start to absorb, and therefore you have to use either a vacuum instrument where the sample and the light, everything is in vacuum, or at least you have to nitrogen purge the instrument. So there is a nitrogen purged instrument upstairs where on the 3rd floor, where you can measure up to 8.5 electron volts. At 8.5 electron volts, magnesium fluoride starts to absorb. And magnesium fluoride is used for the polarizers, and therefore you cannot go higher. And therefore it is difficult to do ellipsometry with windows or anything else beyond 8.5 electron volts. If you want to measure at higher energies, let's say between 10 and 20 electron volts, then there can no longer be any windows in the beam path. You probably need to go to a synchrotron as the light source. And you need to use all reflective optics, which means that your polarizer consists of typically three gold mirrors or 3 magnesium fluoride mirrors.
These mirrors
Glancing incidence. So these are glancing incidence mirrors. So they are not very good polarizers, but you can do ellipsometry up to 25 electron volts using synchrotron light sources. Beyond that, I'm not aware of any ellipsometry setups that go beyond 25 electron volts. So the 25 electron volt instrument is in Berlin. Okay, so then at higher photon energies, you can no longer do ellipsometry, so you have to do reflectance measurements. Or you can do transmission of thin films. As you've seen, the absorption coefficient goes down as you go into the UV, so your penetration depth becomes larger and larger. If you go to the X-ray regime, for example, the penetration depth of X-rays is on the order of thousands of angstroms. So then transmission measurements become possible again to measure absorption coefficients. And you can also do reflection measurements. The reflectivity will be very small, of course, so you may have to go to glancing angle measurements. But if you have reflection data, if you have reflection coefficient data, then you can use chromoschronic techniques to obtain the absorption coefficient from what you have measured for the reflection coefficient. I don't know. Did you have something else in mind, or does that cover what? Yeah. So
for silicon germanium, is really the dielectric function known up to several tens of electron volts?
So there is this book by a series of volumes, 3 volumes by Palik. And Palik has optical constants tabulated on a double log scale from fractions of from 10 wave numbers all the way to thousands of electron volts. And he plots N and K. So the answer is that for many materials, these numbers are very well known. And for some materials, we can measure reflection. For other materials, we can measure absorption. I'm sorry, for some spectral ranges, we can measure reflection. In other spectral ranges, we can measure absorption coefficients. And then we put those data sets together, and with chromoschronic transformations, we can tabulate optical constants over a really, really broad spectral range. Anything else? Well, thank you very much. And Mareike, when is the next lecture? Next week. Oh boy. Okay. I'll see you again next week.